Okay, so next we will show that the space of rationals with the order topology is a second countable space. So proof: a basis for the order topology on the rationals is the collection script B of all open intervals from A to B, where the endpoints A and B are rational numbers. Now let the function f from the Cartesian product of the integers, of the rational numbers with itself, into the basis script B be defined by f of the ordered pair AB is the open interval from A to B if A is less than B, and is the open interval from B to A if A is greater than B, and is the open interval from 0 to the absolute value of A plus 1 if A is equal to B. That is, every ordered pair in the Cartesian product of the rationals with itself determines the endpoints of an open interval in the basis script B. Clearly, the function f is a surjection Now, as the Cartesian product of the rationals with itself is a finite product of countable sets, it is countable and so there exists a surjection which we will call G, mapping the positive integers onto the Cartesian product of the rationals with itself, and hence the composition f of G, which is a map from the positive integers onto the basis script B, is a surjection and thus the basis script B is countable. And therefore the space of rationals with the ordered topology is second countable. So notice that the space of rationals in the order topology is distinct from the discrete space on the rationals, since discrete spaces are not separable and therefore not second-countable. And also recall that the space X with the order topology, or in the order topology, is T2 or Hausdorff. And so the space of rationals in the order topology is T2 or Hausdorff. So we now know two topological invariants of this space. So as an exercise, consider the space Q in the order topology. Determine whether or not the space is connected, and determine the number of isolated points in the space. Now, the standard topology on the rationals is the order topology. So in the absence of a stated topology, when we speak of the space of rationals, it is implied that the topology is the order topology. Similarly, the standard topology on the reals is the order topology. The space of the reals in the order topology is called the real line. Now, our model for the real line comes from Euclidean geometry. And until the irrational numbers were discovered, the Greeks originally thought that all numbers on a line could be represented by rational numbers. and we can rediscover irrational numbers ourselves in a fairly simple manner. We start with a line. We choose an origin. We choose a unit length. And then we construct a perpendicular to the line that passes through the point of unit length. Then we choose a point on the perpendicular that has a unit length. And then the portion of the arc that passes through this point crosses our line, or is a number on the line, somewhere between 1 and 2, and we'll call this x. Now notice that we have a triangle that is a right triangle with a hypotenuse of length x and legs each of length 1 unit. And so in applying the Pythagorean theorem, we have that the square of the number x is equal to the sum of the square of the legs, each of which is 1. And so this is 2. And we will show that there does not exist a rational number whose square is equal to 2. So we'll start with a lemma. Let a and b be two integers. If the integer a is even, then the square of that integer is even. And if the integer b is odd, then the square of that integer is odd. So proof. First statement. Suppose that the integer a is even, then a is equal to 2 times m for some integer m. And so a squared is the quantity 2 times m squared, which is 4 times m squared, which is 2 times 2m squared, where 2m squared is an integer, and hence a squared is even. So second statement. Suppose that the integer b is odd, then the integer b is equal to 2 times n plus 1 for some integer n. And so b squared is the quantity 2 times n plus 1 squared, which is 4n squared plus 4n plus 1, which is 2 times the quantity 2n squared plus 2n plus 1, where the quantity 2n squared plus 2 times n is an integer, and hence b squared is odd. So as a corollary, let a be an integer, then the integer a is even if and only if its square is even. So proof. Suppose that the integer a is even, then by the previous lemma, a squared is even. So conversely, suppose that a squared is even, and assume to the contrary that the integer a is not even, then the integer a is odd. So by the previous lemma, the square of a is odd, but this is a contradiction, and so by contradiction, the integer a is even. Now notice that for every rational number q, that rational number can be expressed as the ratio of two integers m and n, where the integers m and n have no common factors. In other words, every rational number can be uniquely expressed as a fraction in reduced form. So we'll use this fact to prove our theorem that there does not exist a rational number such that the square of that rational number is equal to 2. So proof. Suppose to the contrary, that there does exist a rational number such that the square of that rational number is equal to 2. Then that rational number is equal to the ratio of integers m to n, and the integers m and n have no common factors. And so we have that the quantity m over n squared is equal to 2, so that m squared is equal to 2 times n squared, and hence m squared is even, and thus the integer m is even. That is, the integer m is equal to 2 times a integer p, so we have 2 times p squared is equal to 2 times n squared, or 4p squared is equal to 2n squared, so that 2p squared is equal to n squared, and hence the integer n squared is even, and thus the integer n is even. But then the integers m and n have a common factor of 2, and so by contradiction, there does not exist a rational number whose square is 2. Okay, so we'll end here for today. Next time we will continue to look at the order topology on the rationals and on the reals, and then we'll move on to the subspace topology. So I hope you have enjoyed the 13th lecture. Thanks for watching.